So let's continue looking here at the various types of metabolic processes and reactions that we'll see within the body. So within the body, we're going to have a whole host of different types of metabolic processes. The book unfortunately talks that we have two, but in reality, we have a whole host of metabolic reactions and metabolic processes. We're going to talk about the four principal ones here. The first of which is anabolism or anabolic reactions. In chemistry class, we call these dehydration synthesis reactions. This is where we're going to take smaller molecules, pair them together, and build a larger molecule. This is going to provide the substances needed for growth and repair. Opposite of anabolism is catabolism, and this is where we're going to take a larger molecule and split it into two. This occurs via hydrolysis. In chemistry class, we will call this a hydrolysis or a decomposition reaction. And so let's take a look at how these antagonistic pairs of reactions take place. So we start with our monomer units. They interact with an enzyme, we'll call it a synthase here. And what they do is that from one end of the molecule, we're going to strip a hydrogen, and from the other end of the molecule, we're going to strip a hydroxyl group. And by doing that, we form water, the dehydration reaction, forming our polymer. Now, what's happening is if we want to break this polymer down, we take that same water, interact it with a hydrolase, and we take the large molecule, the hydrolase, and the water together, and we're able to, once again, shear the molecule apart, where the side that still has the oxygen remaining to it gets the hydrogen, and the hydroxyl group goes to the other molecule. And so we end up having this cycle. Now, thermodynamically, an anabolic reaction absorbs energy, whereas the catabolic reaction releases energy. And so normally when we have a synthesis reaction taking place, it will typically be linked with a hydrolysis reaction to provide energy, or one of the next two forms of reactions to provide energy to activate the reaction. The first of these is the isomerization. And so the isomerization is where I change the shape of the molecule without changing the function of the molecule. And so if you notice here, we're taking glucose 6-phosphate and converting it into fructose 6-phosphate. There are other types of isomerization reactions where we change the shape of the molecule that can go about and change the function of the molecules as well. But what we're doing is we're changing the molecule order of atoms without changing the actual number of atoms that are there. The other form is what's referred to as the kination reaction or kinetization reaction, and this is an activating reaction. In the kination reaction, what we're doing is we're taking phosphate and sticking it onto a molecule. And by doing that, we energize the molecule. We give the molecule more energy than it has at its resting state. This forces the molecule to do a kinematic change. And by doing that kinematic change, it provides for the activation step within the pathway. Which takes us to the next concept and just a quick review of concept that we looked at when we looked at homeostasis. And that is the concept of regulation and control. And just remember, regulation is systemic and it's going to involve hormonal and cytokine signaling, whereas control is biochemical and is performed within the pathway. Both of them are going to deal with turning on and turning off regulatory enzymes. The function that they regulate is deemed the rate-limiting step. The enzyme at the rate-limiting step is referred to as the rate-limiting enzyme. And what it's doing is it's controlling for how much energy is necessary for that pathway to take place. Or it's controlling the directionality by which that pathway step takes place. And so let's take a look at this key regulatory step in terms of enzymatic activity. And so what we're trying to do is we're trying to regulate how much activation energy is necessary in order to have the step proceed. That is, we're controlling for the rate of reaction. In terms of the energetic control here, it's based off of an endothermic and endergonic issue. That is, do I have free energy being released, or do I have energy needing to be absorbed? If energy is being released, it's exothermic or exergonic. If I have energy that's being absorbed or taken in, it's endothermic or endergonic. When we look at the way in which enzymes function, it's all about the ability for the reactant to sit into the enzyme binding sites. And so for catabolism, I start with a larger molecule, it interacts with its enzyme, and by interacting with the enzyme, it pulls at the binding site, thereby splitting the large molecule into smaller molecules. Or with the anabolic reaction, where I start with two different reactants, they interact with the enzyme does its conformational change, forcing the two molecules to interact with each other, and thereby forming the larger product. Now, the whole key here is that the product cannot fit into the binding site on the enzyme and thereby gets ejected out. When we're looking at isomerization, the reactant will sit inside the enzyme. The enzyme will do a torsional change, its conformational change, and what it does is as it changes, it stretches out and reconfigures. Whereas with kyanation, I actually have a binding site for phosphate and a binding site for the reactant. And by putting the phosphate and the reactant onto the enzyme will lock the phosphate onto the molecule. Any molecule that's going to stick a phosphate onto it is referred to as a kinase, K-I-N-A-S-E. And so we're going to be talking about a whole bunch of enzymes. If we say the enzyme is an isomerase, it's going to cause a change in the structure. If we say that an enzyme is a kinase, it's going to stick a phosphate onto something. And so let's take a look at a generalized enzymatic reaction in terms of forming a larger molecule.
Enzymes enable molecules called substrates to undergo a chemical change to form new substances called products. Each enzyme acts on a specific molecule or set of molecules called substrates. Each substrate fits into an area of the enzyme called the active site. This fitting together is often compared to a lock and key mechanism. However, the enzyme changes shape a little to fit with the substrate. In the enzyme-substrate complex, the enzyme holds the substrate or substrates in a position where a reaction can occur easily. After reaction, the enzyme releases the products and can go on to carry out the same reaction again and again.
In the enzyme.